Have you ever stopped to think about what's really going on when your favorite apps talk to the internet? It all boils down to this kind of digital handshake, a really cool way for totally separate computer programs to have a conversation. So let's dive in and see how it all works.
I mean, really think about it. When you stream a movie, some server, maybe thousands of miles away, is beaming a massive file to your device, piece by perfect piece. When you're in an online game, your machine is having this constant, super high-speed chat with dozens of others at the same time. How on earth is all of that coordinated? Well, welcome to the world of distributed systems. It's powered by some seriously elegant ideas.
Okay, so before any of that data can fly across the internet, two programs need a fundamental way to just know the other one exists and to reach out. This is the first, most basic piece of our communication puzzle. And that foundational layer is called inter-process communication, or IPC for short. It's basically just a set of rules that lets one running program, which we call a process, send a message to another one. It's the simple core agreement that says, hey, I can send something and you can receive something. This is literally the ground floor for everything else we're going to talk about.
All right, so we know programs can talk, but how? If one program wants to send a message, how does it address the envelope? How does it find the one correct program out of the billions connected to the web?
The answer is a really powerful idea called a socket. In the tech world, we call this an abstraction, which is just a fancy way of saying it's a simple concept that hides a whole lot of complexity. The easiest way to think of a socket is like a digital PO box, or maybe a specific extension on a phone line. It's not a physical thing, it's just a unique destination for sending and receiving messages.
So how is this unique address actually created? Well, it's a combination of two things. First, you've got the IP address, which gets the message to the right computer. That's kind of like the street address of a big apartment building. Then you have the port number, and that gets the message to the right application on that computer. That's like the specific apartment number. You put them both together, and bam, you have a destination that is totally unique across the entire network. So we have an address, and we can send a message. But what are the rules of the road? What's the etiquette for this conversation? Do we need to get a confirmation for every little thing we send, or can we just fire away and hope for the best? This is where programs have to agree on a protocol, which is really just a set of rules for the conversation.
And there are two main styles here. On one side, you have UDP. Think of it like sending a postcard. You write it, you drop it in the mail, and you just kind of assume it gets there. There's no tracking number, no confirmation, it's fast, it's simple. Then you have TCP. This is like sending a registered letter. It requires a signature, you get a confirmation that it was delivered, and you know for an absolute fact that it arrived safe and sound.
And as you can probably guess, this means there are trade-offs. UDP is all about one thing: speed. Since it doesn't wait around for acknowledgments, it's incredibly fast. But the cost of that speed is reliability. Packets can get lost or even show up in the wrong order. TCP is the complete opposite. It sets up a formal connection, it acknowledges every single packet, and it'll resend anything that gets lost. You get perfect, ordered delivery every time. But all that checking takes a little more time, which makes it a bit slower.
So when would you use one over the other? Well, for a voice call or an online game, you're definitely going to use UDP. If one tiny packet of audio drops out, you probably won't even notice. Speed is what matters most there. But for loading a web page or downloading a file, oh yeah, you need TCP. You can't have missing pixels in a photo or a single lost word in an email. In those cases, every single piece of data is absolutely critical.
But hold on, there's another challenge. Imagine one computer represents numbers in a certain way, and the other one uses a totally different format. Even if the message arrives perfectly using TCP, it could still be complete gibberish to the receiver. The programs have to agree on a shared language.
This translation process is called marshalling. Before sending anything, the program takes all its internal data, numbers, text, whatever, and it flattens it into a standardized, universal format. Then, at the other end, the receiving program does what's called unmarshalling, where it unpacks that standard format back into its own way of doing things. It's a clever way to make sure both sides understand each other perfectly.
And luckily, programs don't have to invent this shared language every single time. There are a bunch of well-established standards they can agree to use. Formats like Corba's CDR, Java's own serialization, or the super common XML. These are all just different established languages that both the sender and receiver can agree on ahead of time.
Now, you might be thinking, wow, that is a lot to keep track of. Sockets, protocols, marshalling. It's a lot for a programmer to manage for every single little network request. So computer scientists built this beautiful layer of abstraction right on top of it all to make it pretty much invisible.
And that is the absolute magic of remote method invocation, or RMI. The whole goal is to create something called location transparency. The person writing the code shouldn't have to care if the function they're calling is right there on the same machine or on a server halfway across the world. It should look and feel exactly the same.
So, how does this magic trick work? Well, the client program doesn't talk to the network directly. Instead, it calls a local stand-in object called a proxy. And this proxy does all the dirty work. It marshals the data, it packages the request, and it sends it over the network. On the server side, a skeleton object is waiting. It catches the incoming message, unmarshals it, and then calls the actual method on the server. And once all the work is done, the entire process just happens in reverse to send the result back. It's just an ingenious system for hiding all that complexity.
So we have gone on quite a journey here, haven't we? From the simple need to send a message all the way up to this sophisticated illusion of calling a remote function like it's right next door. Let's just quickly recap all the layers we've built.
It all starts with inter-process communication, the basic ability for programs to talk. Sockets give us the unique address to talk to. Protocols like UDP and TCP set the rules for the conversation. Marshalling provides that shared language so we can actually understand each other. And finally, these high-level ideas like RMI wrap the whole thing up to make it feel like a seamless, easy conversation. See? Each layer builds perfectly on the one before it.
And that right there, that's the ultimate benefit. All of this incredible underlying complexity exists for one reason: to make something that is ridiculously difficult, communicating reliably across a global network, feel simple and straightforward for the people who are building the apps we use every single day. So the next time you join a game or start a video call, you'll know about the intricate, invisible dance of protocols and proxies making it all happen. That digital handshake is what connects our modern world. And now that you know the rules, what new conversations do you think we could build next? Thanks for tuning in.